everyone for joining. And we are recording. Nitin, we are recording.
Yes, ma'am. Yes, ma'am.
So your IP issues, you can take care.
Yeah,
So,
sure.
yeah. So it will be posted in the IGS YouTube channel. So we are trying to create our own digital, library. So keep following that YouTube channel as well, and also Geo-Hazards Lab Facebook page, so that you can get updates. So this lecture, next lecture will be from the industry. So we are trying to make in such a way that one from academia, one from industry, so that the students do get a benefit out of it. Both undergraduate students and the postgraduate, of course, research students. So keep following that and then attend, and it should be more of interactive. So speakers were also taken in such a way that, they'll be young, energetic, and, they'll give you all the things that you wanted. So make it as interactive as possible. You don't need to ask only questions related to technical part, especially students. You can ask them anything like, how to start, how to read a paper, anything, such kind of things also. Make the benefit out of it, what the IGS local chapter or Indore chapter is doing. So with this, I welcome you all again, and congratulations to Ramu and for organizing this. So thank you so much. Yeah, we have our Honorary Secretary, Dr. A.P. Singh also joined. Good evening.
I got late actually.
Good afternoon, madam. Dr. Arun Khare.
Sir, Khare sir. कैसे?
Good afternoon, Khare sir.
नमस्कार तिवारी जी, सिंह साहब नमस्कार.
नमस्कार नितिन जी कैसे हैं?
बस बढ़िया
सर, आप कैसे?
So we just started.
Yes, sir.
Dr. A.P. Singh, we just started. So would you like to say a few words?
Who, I?
Of course, you are our secretary.
I would like to congratulate Nitin for joining us and delivering a very knowledgeable lecture. And we will see how much we are going to get updated from your lecture. So please start your lecture, Nitin.
Yeah, sure.
And thank you, ma'am, for this wonderful support and encouragement. And before we start the lecture, and I would like to ask Kunal, the co-coordinator of this event, to introduce about the speaker briefly.
Good afternoon to all the participants. It's my privilege to introduce Dr. Nitin Tiwari. Dr. Nitin Tiwari is a postdoctoral researcher at the Lyell School of Civil Engineering, Purdue University. He earned his PhD degree from IIT Indore and his ME from University Institute of Technology, Rajiv Gandhi Technical University, Bhopal. During his PhD, he developed sustainable methods to improve expensive soil behaviors and received the Best Research Paper Award from IIT Indore for his interdisciplinary research on soil stabilization using native bacteria. He also received the Young Scientist Award in 2021 from the MP government, from Madhya Pradesh Council of Science and Technology. Dr. Tiwari has published over 25 journal articles in international and national journals and conferences, and authorized 3 books on structural engineering. He is a life member of IGS and a member of ASC and TRB. He served on the AKG-80 Geosynthetic Committee of the Transportation Research Board. Starting this fall, Dr. Tiwari will be joining the School of Civil Environment and Infrastructure Engineering at South Illinois University, Carbondale, as an assistant professor. Dr. Tiwari, please.
Thank you, Kunal, for the introduction. Dr. Nitin, you can take over this platform, and you have a 40 to 45 minutes of lecture time, and followed by question and answers. Thank you so much. Over to you.
Thank you, Dr. Ramu, for giving this opportunity and allowing me to present in the first lecture, like a monthly lecture series as a first speaker. So it's my honor, to be honest, and the best part, seeing Nilima ma'am, AP Singh sir here, and even Arun Khare sir here, it's it's my honor, honestly. Before I start something, I shared a small survey link in the chat so that I can just know whether we have a BTech student or PhD student or MTech student, and I can modify my presentation accordingly while I'm talking. So I request all the participants just click on that link, survey link, which is presented in the chat, so that I can just modify my presentation the way I need to present accordingly. Though Nilima ma'am already told me that there will be a many undergrad students, so I'm taking care of these things. I'm just presenting small things so that you can understand and you can use this presentation as a like, beginning of your major projects or minor projects where you can use. So I request every participants to please just go to the survey link. There are only 2 questions. Just click whether you are a PhD student or you're a student of which area. Like if you are from structures or some other branches, you can most welcome to select. So please do that, please. So let me start presenting. Dr. Ramu, can you see my screen?
Yes, Nitin. We can see this presentation.
Oh,
Please go.
perfect. Perfect. Thank you. So let me take one more minute and see. Perfect. All right. So thank you again, everyone, IGS Indore chapter, and I congratulate all the newly elected EC members for starting a new tenure. And again, thank you for giving me this opportunity to talk about sustainable geotechnical solutions for the resilient infrastructure in the rapidly changing climate. As Kunal already informed you guys, like currently I'm doing a postdoctoral, I'm a postdoctoral research assistant at Purdue University, and soon I'm going to join as a assistant professor to Southern Illinois Carbondale. Okay, so coming to the presentation, I designed this presentation like I'll go with the introduction, talk about what is sustainability and resiliency, because we are talking a lot about these terminologies. I'll also talk a little bit about how the climate change is impacting our civil infrastructure and how we can contribute. And then I'll go to the deep of my research, which I conducted most of the part of the today's research from at IIT Indore. So it will be quite relatable to most of the student who lives around Indore, because I'll talk some site about Indore sites and everything. So it will be very relatable to you. And it will also give you opportunity to collaborate with IIT Indore, because all the facility which I'm going to present today has been used at IIT Indore. So it's like a win-win opportunity for you to collaborate with me as well as collaborate with IIT Indore and access IIT Indore's lab with the permission of Professor Neelima ma'am. And that will be really helpful for you. So I'll talk about the expansive soil and its impact, majorly targeting like a Madhya Pradesh area. And then I'll go to some solutions which we worked on during my PhD, especially like how we use the native bacteria to stabilize the soil, how we use geosynthetic, how we use geotextile, and how we use the silica fume polypropylene fiber, and how we exactly did the physical model testing, the big testing, so that we can find it out how exactly our treatment protocol will work when we have a larger scale testing system. And then I'll give some concluding remark. It's not like a conclusion I'll just give some concluding remark which will give you a research direction which you can opt for your further research. So let's start this journey. When it comes to sustainability is a broadly terms. Like if you go to nowadays any research, the 3 terms sustainability, resilience, and climate change, they are they have become the center of all the research areas in civil engineering. Even in the other area, people are talking about sustainability, people are talking about resiliency, what people are talking about climate change. We need to figure it out. We need to understand, we need to define our definition of sustainability, what exactly we are looking at as sustainability, and then we need to figure it out how we can incorporate the sustainability or resiliency or climate change effect in our research, in our applications, field applications as engineers or anywhere. So when it comes to the UN World Commission definition, they say simply we development that meets the need of the present, remember it, without compromising the future generations need. So I mean, very broadly they say is like you can do anything, you can find your needs right now, you can use natural resources right now, but you need to think about the future generation. You cannot take everything and future generation is not like able to access anything. So like we need to think about it. But when it comes to the functional definition, I think when it comes to the functional definition, we need to think about like how we can balance between the economic growth, environmental care, and social being, while considering even the future generations requirement. So we need to consider the requirement of the future generation, but at the same time we need to think how the current need is met with the economical growth, environmental care, and social being. So if you need to find it out the three functions of sustainability, I would say it's a junction of environment, economic, and society. If you take these 3 points in the core of your research area or anything you're doing, any any work you're doing on everyday's life, you need to think about all these things. And if you can take care of these three things, you are really working towards the sustainability. When it comes to resiliency is nothing but to prepare and plan for the adverse event. We need to ready for any kind of adverse event is coming, be it a flood, be it earthquake, be it wind, be it tornado or anything. Our infrastructure should be ready for the adverse event. That's the definition of NRC. And there is another definition, which is nothing, again the same, prepare and adapt for the changing condition. And we should be ready to recover rapidly. So like it should be like, sometimes you cannot be very resilient towards the flooding because that can be like, a huge, but we should be able to recover from it very quickly. I mean, so we need to divide how we can like withstand during that particular time, the particular adverse event. So these are the things which we need to keep in mind when we talk about resiliency and sustainability. These are the really very important terms, and it should be like at the core of your research area. And why exactly we are talking about sustainability and resiliency? That like there are many if you go to the internet, Google it, why we care about sustainability, why we care about resiliency, you'll find so many ways, so many reasons, so many things are coming, like populations increasing, natural resources consumption and depletions are happening. There is a greenhouse changes, environmental population, ecosystem is changing, like diversity is reducing. But when you see like many events, there is always a climate change which forces us to think about sustainability and resiliency, because climate is changing very rapidly. For example, recently this year, like we had a summer heat in India, and like temperature going plus 50 degrees Celsius. That's something alarming. Like are we ready? Our payments are ready for these kind of a temperature if in future it goes very high, like for example asphalt payment, whether we will be able to withstand for this kind of a adverse event or not. So we need to think about it. Like a week before, we were in a Delhi, especially, we were talking about we have a water crisis, and I was going through the news today, and it says today it is flooded, like the area is flooded just with one rain. Are our infrastructure is ready for these kind of adverse situation or not? We need to think about it, and that's the only reason we really talk about sustainability and resiliency. So in this regard, like UN already developed a sustainable development goal, and these goals are very important. And these are the 17 goals which they designed. But as a civil engineer, we just care about 3 goals which they mentioned. Number sixth goal, which is like a clean water and sanitation, which is like a more into the civil engineering part. We really talk about 11th, which is sustainable cities and communities, and we also talk about affordable and clean energy, which is the 7th number. But when it comes to the geotech part, people, we need to really think about the goal number 11, which is like a sustainable cities and communities. So like UN decided long back, like how we can work on these areas, and we need to really think about the sustainability goals. So let's talk about a little bit how sustainability and resiliency are correlated with each other, and then we'll move forward. So the sustainability is a capacity for protecting ecology, ensuring economic prosperity, and ensuring the society well-being, as I discussed just before. When it comes to resiliency, it is nothing but overcoming unexpected crises. As I say, like we need to ready for the adverse event coming in our life. We need to be very adapted for the turbulent changes. Like if suddenly the temperature is changing, if suddenly the flood condition is changing, if anything is happening, even in sudden, we need to be ready. We need to think about it, how we can fight against that. And then we need to flourish in this chaotic world. I mean, there is no reason to stop. So like we fought with the pandemic like in few years back. So like we need to think about it, how even the pandemic kind of a situation is coming in our life, how we can deal with that. It's sustainability and resilience is a continuity process, and they just talk. I mean, it's a hierarchy. They are the like they are imperative to each other. So like it's not like something like you can take sustainability as a side or resilience in somewhere. They both complement each other. We need to talk about this continuity and fitness, and then we need to work for the sustainability. So that's really very important. As I said, like a climate change, why we are talking about climate change has like many reasons. As I mentioned, the temperatures are increasing, and like normally you can say like world is full of different climatic conditions. Like when it comes to the like for example, this year we have a huge heat waves and a high temperature. At the same time, we have a places where like we are freezing, like, so everything we need to take care of. So the temperature is always a core of the climate change, which we need to think about it. Wind is the another area which, like, luckily in Madhya Pradesh we don't have that kind of a problems, but yeah, there are several reasons where we need to think about like a hurricanes, tornadoes. Like if you talk about my city, in every 2-3 weeks we get a tornado warning. So like you need to go to your basement, be careful about all these things, otherwise your house is like so it's very risky. So like these kind of things, are we ready for this kind of a event or not? So like we need to think about it. Precipitation is the another big reason, like because of the like flood risk is there, sea level rising is happening due to the temperatures effect or greenhouse gases effect. So like we need these are the climate change, like a core of the climate change conditions. And then wildfire, this is another, I mean, not uh, majorly affect the civil infrastructure, but at least overall it increases the temperature, and then subsequently you have a problem. So like these are the major reason areas which we talk about. Especially for my research moving forward, I'll talk about two things. One is temperature, which is where I'll talk about how freezing and thawing affects the civil infrastructure. And second, I'll take the precipitation effect. Like for example, if you have a flooded situation for the infrastructure, how you can deal with this kind of a flood situations. I was trying to figure it out the Indian map, but I could not do that very quickly. So I'm just presenting a US map, and like you can see, I mean, no state is unaffected by the climate change. Like most of the states, they have a fire problem. If you go to Upper Peninsula or bottom, like you have a flooding condition, hurricanes. You can see snow, obviously, like and tornadoes. Like especially, I am here in this region, and we have a tornadoes issues. So these are the problems, and they are really bothering everyone. It's like just a map of United States, but everywhere that's a problem. Uh, very good images. I just try to collect like how really the civil infrastructure is affected by the climate change. And you can see like complete city is flooded, and you can see they're full of, you can see the road infrastructure. In our research group, we work a lot on landslides, and you can see like Uttarakhand we observed so many landslides and everything. So they are the really reasons of the climate change, and we need to consider them. I mean, you can see the government pavement got submerged in the water, and you can see after effects on the pavements also. This is a very interesting picture of 2018. It's near to Michigan State University in US, and the complete city got like a flooded, and you can see the condition of pavements. There was like a small drainage line, and everything completely got collapsed. In the United States, and you can see like this picture is also from the Upper Peninsula in US, and you can see this was a major core city area, and you can see the completely flooded area, and the pavement got washed out. Another picture from the same area, and you can see the condition of just after a small flood event, and the pavement got completely collapsed, and we were not ready for this kind of a adverse situation back in 2015 for the Michigan area. Some other pictures, you can see the complete shoulder of the pavement got washed out. complete city is submerged with the water. So I mean, you can see like the water is creating a lot of like a flooding condition is creating a lot of infrastructure related issues. And are we really dealing with these kind of issues or not? This is I never like this picture to show, but still this is something which we need to think about it. The picture is coming from Andhra Pradesh, and you can see like these potholes. It looks like we designed these potholes in the road, but they're not designed. They're the potholes, and like your complete car can swim inside the potholes. That kind of area they covered. So really, we need to think how we can deal with these kind of situations. And again, environment pollutions, wildfire, other things are really responsible for the climate change. So climate change is a broader, it's a big area. You cannot cover everything, but uh, as a core of your research, as a your minor project in BTech, major project in your BTech, MTech thesis, BSD thesis, even as a researcher, we need to think about how we are bringing something positive towards the sustainability, resiliency, and the climate change. So let's go to my research, which I conducted at IIT Indore, and it is majorly focused on expansive soil. So I'll talk about how expansive soil really affects the civil infrastructure and how we can deal with these kind of a problem. So when it comes to the definition, because we have so many BTech student also, so I'm just going a little bit like, the fundamental for the students, but I mean, seniors can like, excuse me for that. When it comes to the expensive soils are the clay-rich soils. Like they have like a majority of the particle size distribution. If you see, they have a clay particles. So like more of your soil will be clay particles. And the problem with the expansive soil is volume change. So like, for example, the moment there is a moisture variation, if it is going high or low, anything, there will be some irreversible volume changes, and that irreversible volume changes causes a soiling effect and shrinkage effect in the soil. When it comes to these, like for example, if you have if you have a very heavy structure, these small minor changes will not affect you. But when it comes to the pigments, like if you have a pigment, they are very light structure, they don't have their overburden like too much. So like if there is a minor soiling or minor shrinkage, you can easily see what kind of a soiling effect or cracking, like a shrinkage effect is coming. So they are really area of a concern. Like most of the time, it is a core of geotechnical research. Many people are working in this particular area from long time, and still a lot needs to be done. Uh, I just try to show the expensive soil site. This is the Malwa Khedi in Indore, and you can see the condition. I'll show you some more pictures of this site, and you can see these. This is kind of an unpaved road, like a completely, and with just water. You can see like potholes are coming, like condition unevenness in the road. You can easily observe. So just for the students of the BTech, if you have not gone through at the Geotech, the clay particles, when I talk about the clay particles, any particle which is less than 2 microns is considered as a clay. And in the majority, if like in the expansive soil, the majority of the particles comes from the clay particles only. And this is just based on the ASTO classification. There can be a different classification. Some classifications even consider 1 micron as a clay particles. So you need to think about it a little bit, but these are the general soil particle classifications for your understanding. Coming to the really the expansive soil effect, and you can see this is also coming from Madhya Pradesh, and you can see this road like a shoulder failure, shear failure here. The many potholes are coming. These are the reasons of expansive soil completely observed. This is the image is coming from Kasarghat, Mumbai, India, and like I think it has been taken in 2020. And just it was a new road, and just after one rain, I guess, or second rain, the things happen, and you can see complete shoulder. There is a shear failure here, and you can see observe there. I mean, if you can see this area. Okay. If you can see this area, the person is inside. It's like, I mean, you can understand the cavity size. This is the another picture coming from the same Malwa Khedi Indore site. You can see me also here. Like you can see like how people are living. So really, I mean, are we giving the better social? Like we talk about sustainability resilience, but are we giving a very when I say sustainability, it's like your society should be like, we need to think about the well-being of your society. And you can see like the things are really not good. Like, so are we really walking towards these kind of a situations? And I'm happy like Nilima ma'am asked me to visit these kind of a site, see the problems, and then we start with work on expansive soil. So let's talk about Indian scenario a little bit. I'm not talking going in the deep discussion about that, but if you see the expansive soil distributions, like almost a 1/5 area of a country is covered with it's a huge area covered with the expansive soil. And major, if you go to the major states like Madhya Pradesh and Maharashtra. When I talk about Madhya Pradesh, I'm including Chhattisgarh in this data because the data is coming from 2012, and I don't know why they are like, they reported the both data together. So like even the Chhattisgarh part is covered in that Madhya Pradesh area. And you can see like vast majority, like a 27% and 21.3% of the total expansive soil distribution is covered by the expansive soil. And even if you see the Madhya Pradesh, you can see most of the area is covered with the expansive soil. Maharashtra, you can see. So generally the expansive soil, they are really good for the farmers. Like farmers love it. We also call it as a black cotton soil because it's very helpful for them to grow the crops and everything. But when it comes to the civil engineers or especially the geotechnical engineer, we say they are the enemies, to be honest, like because whenever you find expansive soil, you're like, oh, now we need to go this, that, like it's like ultimately people think about we need to remove this material from here or we need to stabilize this material before using it. You cannot just directly construct anything on expansive soil, and you need to think with what kind of a soil and behavior is coming from the soil. So this is the condition of the country. For these, I divided like my solutions in the 3 categories, and I'll talk one by one. So first, let's talk about microvalley induced calcite precipitation treatment. And like we have like Monica is here. Like she is really a good resource person for you guys if you are in Indore, because she worked a lot on MICP part and like having a very good experience with sand particles stabilization. At IIT Indore, we worked a lot on MICPs. Like, so I mean, you have a good area to work. The most of the research, when it comes to when we started this work, so my colleague, Dr. Meghna, she was working on the sand particle stabilization, like how we can bind set of particles for the liquefaction. And at the same time, me and Dr. Nilima ma'am discussed like how we can incorporate this kind of situations in the clay particles. Is it possible? Because the most of the MICP, so let me talk a little bit MICP, then I'll explain why how it is difficult for the people. So coming to the motivation, the pictures are coming from BM Das. I'm really thankful for like his support for these images. And you can see like these kind of structures has been generally observed near sea source or the water body, and people started thinking like why this is happening. And later they realized that some bacterial microbially induced calcite precipitation happened, and they bind the sand particles and they form the good structures. So people started taking this as a base of the research and started finding which bacteria can do microbially induced calcite precipitation, and then they figure it out the structures. So like field is not really new, to be honest. I mean, people are working since past 20-25 years, but when it comes to the expansive soil stabilization or the clay part stabilization, because it is really challenging, so very limited people have worked in this area. So how exactly this happens? Like, for example, you have a soil particles, like you can see in the first image, like you have a different grain size distribution. I'm sorry, I just created this image last night, so may not be very appealing, but just for the understanding. And there are always some bacteria present inside the soil. So you need to figure it out. Whether these bacteria can be helpful or not. But either you need to use the indigenous or native bacteria already present there, or you need to figure it out if you can add some external bacteria and find it out whether it can work for you or not. And these bacteria, like a gram-positive bacteria, especially have a capabilities to produce the calcite precipitation. And once they produce the calcite, this calcite work as a binder, and they bind the 2 soil grains or 3 multiple soil grains, and give the stabilized structure. So this is kind of a in general MICP mechanism work. Like you have a soil, you have a bacteria, you either you added the bacteria or you simulate the exact bacteria of the site, and then you use for the stabilization. So that's the in general process. The problem with this particular method, this is very good when it comes to you can pour the solution like so for example the sandy particles, you can easily they are highly permeable, so like you can pour the solution and continuously solution can flow from one side to other side and it will work out for you. But when it comes to the expansive soil, the problem with the expansive soil is like they're really not like they're like a impermeable layers, and since they are the impermeable layers, it is really hard to provide these solutions the way we provide in the sandy soils and everything. So like we need to, so that's the one challenge. Second challenge, most of the sand particle, when we do the sand stabilization, we use the bacteria which is coming from the external side, like you are providing the argument, the bacteria, like taking the bacteria from somewhere else and providing the bacteria there. The problem with that, ultimately, when you're adding the bacteria which is coming from the different side, you are disturbing the ecology of the surrounding. And when you are disturbing the ecology of the surrounding, like it's not good for the environment. So like we need to think which if we can use the bacteria which is already there, it will not disturb the ecosystem of the area. And that's how we came to the idea. Let's simulate the bacteria which is already present in the soil. We are not going to add any new bacteria. And second thing came in our mind, let's figure it out if it can work for the clay material or not. And we really worked on that. So how we did it? So we collected a sample from a different sites. And after collecting this particular sample, we generally in the MICP, we create two solution. We call it as a culturing solution and cementation solution. I'm not going in the chemistry of it because you can read anytime about the chemistry whenever you're working. But the core or the crux of the area is you have a two solution. One is like a culturing solution, culturing media, we can say, and second is your cementation solution. So what we did, we have taken the cultural solution, we prepared the cultural solution, which considers like a nutrient broth and everything, and we put the soil inside, and we want to just increase the bacterial growth inside that. Like you can see these kind of a biofilms are coming in the image number one. So and then we calculate the solutions OD. OD is optical density, or OD 600 we calculate, and we see if there is a bacterial growth inside the sample or not. So like we prepare this kind of a sample, keep it for some time, and we keep on checking if there is a bacterial growth or not. And once we find it out, yes, there is a bacterial growth, we take this take the solution, we culture that solution in our environment chambers and everything. And once we culture that solution, we take the bacterial palette from that cultured solution, and then we prepare the large quantities of the solution. So we are not like we don't need to simulate the every time the complete bacteria or cultured bacteria. You can harvest that particular bacterial strain from the native bacteria, and then you can use that particular. And this is just after the 4 days, like how your expansive soil will look like once you'll mix it. So the problem, as I mentioned, like how the people with the sand work, they take the sand in some pipe or any kind of a box, and they just pour the solution from the top. They try to extract the solution from the bottom, and slowly the calcium precipitation happens, soil binds and everything. But this is not possible with the clay. You cannot cut. I mean, few of the people must have experience with the permeability test. If you have to do the clay permeability, it takes a lot of times. Like you spend a lot of time for that. Even if you do the triaxial for the saturation of the clay element, clay particle, it takes a lot of time. So like how we can do that, like that's not possible to provide a solution for sure. So what we did, we decided to go with the conventional method, how the cement treatment or lime treatment works. So what they do, they mix the lime and cement treatment in directly in the soil, and then they compact or cure the soil. So we decided let's go with this same system. So like what we did, I hope this is visible. If not, I'll just zoom it out a little bit. So you have a soil sample, as I mentioned initially. You have a soil sample, you take this soil sample, culture the bacteria. After culturing the bacteria, what we do, we mix this particular solution directly inside the soil. So we at the optimal moisture content, like the way we do. So, and we keep on provided the solution until 4 days. Like, but we keep on checking if we are losing some moisture content or not. If you are losing, we add the another solution. And then we prepare the UCS samples, like compact the way we do the compaction, and you can see these kind of samples are appeared. And once it is done, the treatment process is done. So we do for the 1 day, 2 day, 3 day, and 4 days. So like the way we do treatment, 7 days, 8 curing and everything. For the biomineralization, 4 days are enough. And once we did this, and then we tested for the mechanical, like unconfined compressive strength or split tensile strength. We did the consolidation, and then you can see these kind of some images. I'll talk about it. I really want to talk to the students, especially about these tests, because these are the important tests. Generally, whenever we are working, especially in the private colleges of Bhopal, I have a very rich experience of 4 years of working in the private college in Bhopal, Madhya Pradesh. Like we generally do CBR or UCS at our labs, but we never think about it. We never think how we can incorporate the microstructural effects so that we can understand the mechanism. And these are the small these are the facility which is available in our area neighborhood, like IIT Indore. They have very good facility for these kind of a test. So let me talk a little bit about every test. So the calcite content test is very small equipment, like people can have it at their institute also. And we just check how much calcite content is present once you do the testing. pH and electrical conductivity is responsible. pH is very important for your cementation effect. So like we need to maintain the pH in the treatment process, and electrical conductivity just indicate whether the chemical reactions are taking place or not. So we need to think about it. The XRD is another important test which you can look into it for the minerals analysis, whether these kind of we are talking calcite is formed, this is formed, that is formed, whether they are really formed or not. We need to go to the XRD and check, yes, this kind of a mineral is present in that or not. We do the FTI analysis. You can access to any school and like go and check FTIR of your material, and FTIR just indicate what kind of a chemical bonds changes are coming into the sample and how you can utilize it. And scanning electron microscopy, which is SEM. SEM is nothing but it's like a X-ray we do for our body. So similarly, we do the X-ray kind of a situations to our soil sample, and we see what is happening inside the structure, whether the calcite is really formed or not, whether the soil particles bonded or not. These kind of a research understanding we do. So these are the very important tests which you can explore from your neighborhood colleges or university or area, and they will be really, really helpful for you to understand what exactly happening inside the sample. Just a minute. Okay. So let's come to the technical part, how we did this particular research. So we have taken the 3 different soils. We call it as a S1, S2, and S3. When it comes to S1, S2, S3, they are the black cotton soils. So we say is basic, and they're the natural soils. So we have not done any kind of a modification inside that. And then we modified 3 more soils, which is like a S4, S5, and S6. S5 and they are the modification of each soil. We added the 30% of the bottom ash. So bottom ash is like a industrial waste, and it is, I mean, you can find it out. We have almost 7, 8 thermal power plants, and I still remember we visited with Nilima ma'am to several of them, and we visited that as dikes, and we figured it out that that's a really pond ash, and bottom ash is a big problem, and we use that bottom ash, to be honest. So we modify with the 30% bottom ash. Like we have, so now we have a total 6 months. Why we did this modification? The intention was 2. Number 1, if we are using a bottom ash have lot of contamination. Like we need to figure it out, like whether since the micro MICP is also work out for the contamination immobilization. My colleague Dr. Meghna worked a lot in that area. She published a really good paper in that. So that's the area if you are using. And the second challenge was, if you are using a bottom ash, ultimately you are changing the grain size distribution of our soil, and it will be really good for having a MICP treatment for the large grain size material. So this was the idea. We have also taken care of like a free soil index. If you check, we have taken the wide range of the free soil index. So with modification, I mean, from 25 to we have 120%. It's like a very low soiling pressure soil we have, and we have a very, very high, like a 120. Not too much high, to be honest, but at least we have a wide range of the soiling index, so that like we can see the treatment which we are doing it is really robust. Even if you see the clay content, we have like a from 71% to almost a 40% of clay content in the soil. So these are the very important parameters when we are doing this kind of a research. We need to figure it out. It should be widely worked out. It should not be one area, like one soil, one and finish it. No, there should be a widely accepted, wide range of the material we need to take and figure it out. Okay, so after treatment, as I mentioned, and then we did the all kind of Atterbuck's analysis, and we observed initially our soil used to classify under CH category, which is highly plastic clay, but with the treatment, it went, most of the section went to the low plasticity clay. So I mean, it shows like ultimately we are changing the Atterbuck's limit, which is a positive indications for our treatment. I mean, it shows at least on the plasticity side, it is working really well. Then we move to the other area and we see, let's check what exactly is happening at the, can I get rid of it? Okay. Anyways, so we check soiling pressure. As I mentioned initially also, when it comes to the expansive soil, the swelling and shrinkage is the two problems. So our target was to let's check with soiling pressure. And you can see initially, just to clarify, if you're not able to observe it, initially you can see the soil pressure, then there is a soil strain, which is with the line diagram. And these black dots and the other dots you're seeing, they are the free soiling index. So you can see initially, for the black cotton soil, initially we had like a very, very high soiling pressure. I mean, you can observe here almost more than 220, 225 kPa. And it went down to the same soil at a 3-day mellowing period. Most of the things, and after that it is not working well. So you can see that from 220 we reached to almost a 50 kPa. So like a huge reduction in the soiling pressure. But at the same time, if you see when you added the bottom ash, it already reduced to 100 kPa. And even if you do the treatment, it goes really down and it came around 5 kPa. So like you can see, initially from the soil, which is having 220 kPa of the upward soiling pressure, you're reducing too much and going just a 10, 15 or minimal soiling pressure, to be honest. Same goes to strain and same goes to free soiling index. So all three parameters worked out perfect. Let's move. So now we went to the calcite content, like if it is working, whether the calcite is really forming or not. And we observe, yes. So initially we had almost 0% of the calcite. In the normal soil, almost 1.2, 1.3% of the calcite content in formed. But when it comes to the bottom ash, because bottom ash is also helpful for the cementation effect and everything, we achieve almost a 5% of the calcite content, which is really, really huge for the binding and everything. So like you'll find like a rock kind of a soil sample once you'll do that. And at the same time, whenever the changes are happening, the pH is maintained and your calcite content is like, your electrical conductivity is also moving in the same directions. Okay, so then we thought, let's go to the microstructural analysis, like how the microstructure or chemicals are working. So the first thing which I told you, like FTI analysis. So this is the first image is the FTI analysis. And you can see initially we have a lot of SiO bonds, like for the untreated soil. And with the treatment, you can see it is used. Like ultimately, calcite needs to be formed from some of the materials. Like you can, it reduce, which is a positive indications. You can see the CO bond is also decreased, which is a positive indication. And at the same time, you can see hydroxyl groups like here, they are slowly depleting. So like these kind of representation shows like, yeah, whatever we are talking about, it is really functional. Then we went to the SEM, electronic microscopy, and we checked like this is like a normal untreated soil. So like you can see the clay particles attached and there are a lot of cavities. But at the same time, after the treatment, 1 day, 3 day, and 4 day, and you can see a lot of calcite content formation you can observe in the images. So it shows the treatment which we are talking, the things happening, they are really, really working out inside the samples. Let's move to the another area. And before moving to the other area, let me tell you, this particular research received Indian patent this year only. And we are really, really, like we submitted in 2020 and within 2 years, we got an Indian patent for this particular research. So once again, thank you to Nilima ma'am for encouraging to do that. let's go to the another area, which is a very traditional method and people are using it. So I thought like it will be really good chance to share with the undergraduate students and they can use these kind of a treatment. So we use the geotextile and geogrid also. So like overall, this come as an umbrella of the geosynthetic. So geosynthetic material, and under the geosynthetic, we have a different material with a geotextile and geogrid. So today I'll talk about geotextile first, and then I'll move little bit about the geogrid also. So what we did, I mean, our target was again the same. So how we can reduce the swelling pressure. So what we did, we used the multiple layer approach. So like you can see these kind of like 1, 2, 3, 4, and 5. So like we want to see if we place the geotextile layer. Geotextile is like a cloth. Okay. So if you take that cloth and just install in this field, how it will impact us. So like we worked out and we figured it out. If we place it the different depths, like for example, 1/3, 2/3, half, and bottom, how it will affect the swelling behavior. As obvious, if you place at bottom, it will not work out really well, but the drainage will improve for sure. So we places at the different prices, and then we conducted the two tests, especially back in days when I was doing, we didn't had like a triaxial, so we could not do the triaxial, but we did the UCS test and upward swelling pressure. So upward swelling pressure test is nothing. We use submerge your entire specimen and observe what kind of upward pressure are coming from the soil. And we also did the last direct shear, because if you see the small direct shear, it's like a 6 centimeter by 6 centimeter. But we did with the 30 centimeter by 30 centimeter box, so that you can have a geograde, geotextile, you can anchor it and do the test. And this is how we did it. Okay, so let's talk about the results directly. Initially, the soiling pressure of our soil was around 60 to 70 kPa. And you can see with the with a different depth combination H not H, you can see we approach, I mean, most of our sample goes like less than 10, 15, or even if you see most of them, they are less than 20 kPa. So from 80 to 20 kPa we reduce. But you can see like a few of the samples are, few of the places are performing really well. I'll talk about them like exactly in the next figure, which is performing really well. But you can see initially the very high soiling pressure, but with time you can observe the very low soiling pressure. Same goes to how much percentage of the your sample is enlarged. And you can see initially there was a huge like a 3.5% of the enlarged like length enlarged in the for untreated and bottom treated bottom place soil. But you can see for the most of the other one, they are just less than 1% of the soil. So what it means, let's see. So what we did, we plotted a percentage soil ratio and soiling pressure ratio. So we divided with the like a complex your control section. And you can see for the control section initially, like for both, it's 1. And if you see these last one, so like you can see H1 is nothing but 1/3, and H2 is half, H naught is top. So it shows whenever you place your sample at the 1/3, like if you need to go with the single treatment, if you place it at 1/3, it will work out for sure. If you place it at top, like and either at 1/3 or at the half, it will work out really well. Even if you place at the bottom, but bottom, I mean, I feel they are the almost the same values. You can observe here, they are almost the same value, so not much difference. But only your drainage will improve, so you'll have a low soil percentage. But for the soiling pressure, it will be almost the same. So not really this one, but if you go to these 3, 4, they really perform well. We also did the unconfined compressive strength, and you can really observe initially we had just around 130, 140 kP of the UCS value, and it went up to like a more than 350 kP of the value. So like these results shows like really, I mean, not only the soiling behavior, even the strength behavior can be controlled with this kind of a treatment. Let's talk about the last second last section of the presentation, and which is like a silica fume treatment and polypropylene fiber reinforced, which is like a traditional treatment, like a cementation treatment. So for our research, we use not only the silica fume, we use the three industrial waste. One is silica fume, bottom ash, and pond ash. But for the sake of my time, I'm just presenting a silica fume, and they will be the same research, like nothing changed, only the material will change. And when it comes to the polyprop fiber, we use two fibers: polypropylene fiber, which is like a plastic waste kind of a fiber, and second we use the the natural fiber, which is the coir fiber. So we use the coir fiber also. But I am going to present just two, silica fume and polypropylene fiber. Even for the geotextile, we also use the natural geotextile, which is the coir geotextile, for the same research, everything, but with the natural fibers. Okay, so let's talk a little bit about the mechanism. So you have expansive soil, you add polypropylene fiber and silica fume inside. So you mix them well and keep it in the humidity chamber and everything. So this is how in general, like you have a big soil particles, you have a fiber, and at the same time you have a silica fume inside. The moment you do curing, so the curing play a very important role, and we'll talk about this curing. So we use three curing system, which is like a moisture control curing, gunny back curing, or water submerged curing. And once you do the curing, water comes in the contact, hydration take place, and you'll find the CHS gel kind of a formation. They bind the soil particles as well as they bind the fiber to the soil. So like ultimately you have a solid skeleton of the soil. So these kind of like they will be filled in the cavities, and they will also bind the soil particle with the fibers, just a representation. For this research, as I mentioned, I'm going to take the chemical treatment with silica fume, but we use the pond ash and bottom ash also. Polypropylene fiber, here we consider two, flooding effect and freezing thawing effect. We have taken 7 days, 14 days, and 28 days curing, and we have taken the three type of curing protocol also. So let's talk about one by one. When it comes to the curing, we use the gunny bag curing. Gunny bag curing is like a jute bag. So you just wrap your samples inside the gunny bag, keep on providing moisture content, so they should not be dry, and just do the curing for 7 days, 14 days, and 28 days. When it comes to the submerged curing, you wrap your samples with the aluminum foil or something. You submerge them inside the water and see what kind of a treatment is coming out of it. So it's kind of a good treatment protocol. And then the moisture curing is like you have a control environment. In control environment, you are keeping your samples with the fixed humidity. We have taken 100 plus minus 5% of humidity, and the temperature 20 degrees Celsius for the treatment. Okay, so coming to the test, again, we did the same set of a test. I'll not talk really much about it, but like a calcite content, pH, electrical conductivity, XRD, FTIR, and SCM for the microstructure. When it comes to the mechanical, we did UCS, STS, and we did ultrasonic pulse velocity and constant volumes, like you are seeing these tests. And these are the sample you can see in the freezing thawing chamber. So there are limitation of the test. I'll talk about it because when you put them inside the soil sample, the water, and go for the freezing and then thawing. So the moment you go to the freezing, confining stress is really unknown. You don't know because it's a freezing environment and you really don't know what is the confining stress at the particular condition. So this test is really need to be rethink as a whole community, and ASTM is really working on it. I just a day before the study, I had a meeting with TRB, and in TRB we were talking about this test improvement. So soon you people will heard ASTM will have a new protocol for freezing thawing analysis. So we go from plus 20 degrees Celsius to minus 20 degrees Celsius so that we can understand if there will be a different freezing thawing cycle, what will be the impact on the infrastructure. So you can see I'm just presenting one result with the 28 days curing and all the methods of curing we use. So there will be some limitation, but you can see initially we had very less 130, 140 kP of the unconfined compressive strength, and we achieve almost 5,000 kP of the strength, which is a huge increment with the 8% silica fume and 0.5% and 0.25% of the bottom polypropylene fiber. And the best part, when you use the silica fume only, you can see these kind of a brittle failure is coming, though we have a high strength, but low split tensile strength. And at the same time, when you add these fiber, the fiber work as a bridge, and it will give you a more solid soil skeleton. Same goes to calcite formation. Initially, we had 0% calcite, and you can observe we had a 0.8, 0.1% of the calcite. And same goes to the other electrical conductivity and everything. So you are observing the improvement in the properties. Coming to the SEM analysis, this is very important. I'll just enlarge a little bit for you. So you can see initially we had a lot of cavities inside the samples. Exactly, you can see these kind of kaolinite mineral, montmorillonite mineral was observed inside. You can see a lot of cavities are coming here. But with the treatment, you can see we really like a clay flags. filled of CHS gel, this completely layered clay particle you can see. At the same time, you can see initially we had these kind of a dense matrix, but we are observing a we have a cavities, but we are observing a dense matrix. We have also taken care of the fiber content. Fiber is really interesting to note. If you see initially the fiber is like a PP fiber is a layered structures. And even in this layers, the CHS gel get filled, like you can see these kind of a CHS gel, and you observe really like this kind of a stiff PP fiber bond with the soil particles and CHS gel, they are binding together. And even when you do split tensile test, this image is just after the split tensile test, you can see this fiber is really helping for giving the resistance towards the splitting. So we really observe that, and you can see even without treatment fiber, you can see the fiber condition. It's like really bad. So with treatment, even we are getting a strong fiber bonds. And at the same time, you can see like a lot of CHS gel is flowing. You can see a very good CSS formation inside these soil samples. Okay, so let's talk about, yeah, I'll just finish in a few minutes, like maybe 5 minutes. So soiling behavior, you can see again, we from top, we from 60-70 kPa to we reduced to like a 30-40 kPa. With this treatment, we observe the CVR. You can see like an increment in the CVR values as well. This is a very interesting, since I talk about the clay particles, clays like soiling, we did this shrinkage analysis also. So like this is like your mercury displacement pads which we use in the lab. We did the a very nice analysis using image processing, and we figure it out how the cracks or shrinkage is taking place inside the samples. So we did the complete image processing analysis. It was really nice, and we can employ that kind of analysis in the larger area, taking the pictures from drones and do these kind of a test for the large sites also. Coming to the large scale physical model, I go very quickly. So whatever from the lab we found, they are the optimum. We use them as an unbound payment, and like we use the untreated subgrade with the biaxial geograde, triaxial geograde, and geosynthetic geotextile. And the same goes to the we treated with polypropylene fibers, silica fume, and the combination. And here we simulate the 20 days, 20%, 30%, and 40% of the flood conditions. And we use geograde and geotextile. The test section was 2 meter by 1.5 meter by 0.7 meter. We used the static plate load test, and we conducted 16 test section for this kind of analysis. So this is the schematic of that. Like we had like a plate load, this kind of a chamber, like the box. This box is still present at IIT Indore. If anybody wants to use, please take a permission from ma'am and do that. So we treated, this is the silica fume treated subgrade. We put the geograde layer, these kind of a layers, and then we earth pressure cells and everything, and we tested and we figure it out. So I'll not go really in deep, but you can see in even with the treatment, we are going with the 500 kPa pressure, and you can see vertical settlements are reducing in every condition. So you can see even like for initially 50 mm of the displacement, it goes back with the silica fume and polypropylene fiber with almost 10-15. So like a huge reduction. Same goes to the stress bulb is reducing. So like the stress distribution is also less. Even if you go to the severe flood condition, the vertical normal untreated samples goes to almost 90 mm of the displacement. But with the control environment, you can achieve almost a 10-15, the same as the mild. So like ultimately your treatment is working well. So let's go to the concluding remarks, which is really important, as I think. So I think the rapidly changing climate situation is a need of the hour. We need to think about sustainability and resiliency really as a core of our research area. We need to explore the innovative geotechnical solutions to enhance the infrastructure's durability and adaptability, like a local solution, to be honest, what kind of a waste is available in your area, what kind of a fiber is available, what kind of a treatment you can provide. So we need to go local and find the solutions for the geotechnical. I mean, we need to be site specific, to be honest. We need to integrate very interestingly the environmentally friendly materials only, which can mitigate the climate change effect. We need to focus on the solution which can address the immediate challenge. Also, it can contribute for the long term in the sustainability. So like if you're using the waste, it's really something you're doing for the society. We need to work on the interdisciplinary collaboration, like need to find it out, like for example, MICP, like a bio people, chemistry people, and everyone is working. So similarly, you need to think about, and ultimately, we need to, as a researcher, as a engineers, we need to think how we can give the robust, reliable, and resilient infrastructure for the future generations too. With this, thank you so much for giving this opportunity again. And any question?
Thank you, Dr. Nitin, for this wonderful lecture. Definitely, students might have enjoyed the way you presented all the starting from the problems and all. So here the two things we'll finish it. Some questions have been received in the chat also. After that, Dr. Amish Sharma, IGS Indore Chapter Honorary Secretary, will give the vote of thanks. Dr. Nitin, can you see some charts in this
I can.
chat box?
Yeah.
Should I read it for you?
I just opened. I can do that. The performance of the bacteria stabilization clay compared with the clay stabilization lime cementization. Yeah. Thank you for the very interesting question, Professor Sharma, regarding how we compare with the cement treated and the bacterial treated. So we initially compare with the pond ash versus the bacteria, and we get even more strength when it comes to the MICP treated samples in the as compared to the pond ash. But we have not really compared with the lime treated or cement treated. So need to be figured out. But when it comes to the pond ash, yes, we had a better strength as compared to the pond ash treated. By the term climate refugees, I mean migration of the people from one place to other due to the created by the climate changes, extreme variation of the temperature. I like to ask the speaker to tell something about the climate refugees, which has got bearing with the climate change. To be honest, that's not a that's not something I really worked on. But yeah, people are moving due to the temperature issues, like migrating from one place to other place. So that's what I meant. We need to bring the sustainability and resiliency towards the climate change so that you can control the climate. And once you cannot live with the 60 degrees Celsius for sure, right? So you need to figure it out from your methods how we can reduce the temperature of that particular area. So though that's not really I worked on, but in general, that's the comment from my side. I think, Dr. Ramu, we have just two questions. Yeah. Oh, what is the name of the bacteria and average dimension of the bacteria used for? Okay, so Praveen, good question to be honest, but we have not used any external bacteria. We use the native bacteria, so we have not figured it out. We just find out, is it gram-positive bacteria or gram-negative bacteria? So that's the gram-positive bacteria, which is used for the MICP treatment, but nothing to do with the identification. But majorly people, when they use the sand particle, they use Pasteuri, Sporcina, these kind of bacteria. You can definitely refer the research of Meghna Sharma, and she really worked really well on that area.
Thank you, Dr. Nitin. I hope many students have a lot of questions. I suggest them to visit Dr. Nitin's profile and then get back to him. I'm sure that he will answer any of your technical questions and even further suggestions from him. So I request Dr. Amit Sharma, IGS Indore chapter, to give the vote of thanks. Over to you, Dr. Amit. Thank you.
Thank you, Dr. Ramu. Sustainable development is the need of today's era. On behalf of IGS Indore chapter, I want to give my heartiest thanks to Dr. Nitin Tiwari ji for giving insight on sustainable development and innovation done in geotechnical field. I am also thankful to our chairperson, Dr. Nilima Satya Madam, for providing all the facilities for conducting Geo-Horizons lecture series first lecture. I am thankful to Dr. Ramu and Engineer Kunal Gupta for taking all the pains for conducting lecture. Finally, to all the participants and all the persons who are directly and indirectly involved in successful completion of this lecture. Thank you very much.
Thank you, Dr. Amit ji. And one more point here to summarize that Dr. Nitin has very well explained the problem definition of this expansive soil, followed by treatments, various treatments available to treat this expansive soil, especially in the Madhya Pradesh region. And I'm sure that all the undergraduate student has received in a very good way. And it's a very fantastic presentation through the images and all the schematics. So Dr. Nitin, thank you so much. And we look forward to hear from you in several vacations. And I also thank Professor Neelima Satyam and even Dr. A.P. Singh from IGS Delhi to join this event. And this is the first event we started and hope that it will go further ahead. Thank you so much. And I now request all the audience to leave this session. Thank you so much. Thank you, Dr. Nitin.
Thank you, Dr. Amu, for this opportunity, to be honest. Thank you so much.